Hello, and welcome to another brief video lesson, Photometry, Aperture Photometry. When measuring the flux or the light output of a star as it reaches us, there are a few methods to accomplish this. Two most common are aperture photometry and point spread function. This lesson will focus on aperture photometry as it is the most accurate in a non-crowded field environment. A star is a point source. But due to the atmosphere, the light on the CCD gets spread out over the number of pixels considerably greater than it would have had the Earth's atmosphere not diluted this light or spread this light out. To extract the brightness then from this star on the image, we have to understand the star's contribution to all the pixels in the area and what the background sky's contribution is. Since the background sky is not always perfectly black, there is some bias introduced by that. We separate that out through a process called aperture photometry. So this is the measurement of light which falls inside of a particular aperture, usually circular, can be otherwise, and compares it to a background source. So here's the process. Most commonly we have a circle, and we place this circle, the aperture, over a star. And if you notice there, the star has some of the sky background in it. It has the star itself and background. Then we have another aperture that measures just the sky. We then subtract these two, and we are left with just the star value. So the star in the sky minus the sky equals the star, and that is the fundamentals of aperture photometry. So what is an aperture? It's really nothing more than a circular ring. And we have three of them, and we look at them in this way. The first one is the measuring aperture, and we call that just simply aperture. Light from the target and the background sky is included in, and that's right here on this graph. Next, we have the null or the dead zone, and this is a region that separates the two areas that we're measuring, creates a buffer between them, and that's here. Finally, we have the sky annulus, or called the annulus, which is light from the background sky, and that's what we have here. With the aperture defined, the process is as follows. The pixels within the measuring aperture are summed to calculate the total signal of the target, and that includes the sky and the target. The pixels within the sky annulus are summed and then subtracted from the values, and that gives us the total star. Selecting the aperture size. The starlight requires you make an aperture large enough to include all of the light from the star, but small enough not to have uncertainties. In this example here, we have another star which is biasing the information inside the aperture. That would be too large. The size of the aperture is the key to success. Too big, you capture other objects. Too small, you don't receive all the counts that include the target and the sky background. So in the first we see it's too large. In the second one, it is just right. We have the star and then just the background in the outer annulus. This shows an example using graph and pixelized type view of what it should look like. The star in the middle with some background sky on the back. In short, understanding aperture and aperture photometry is key to all studies in photometry. You will use this process time and again to measure the flux from not only your target, but from the background sky. Thank you for your attention, and we look forward to seeing you in another brief video lesson.